We're going. All right. Hi, Stanley. I have a relatively short lecture today, and it doesn't really break any new ground. We talked about the doubly connected edgeless data structure last time, and I want to look a little bit at implementation issues that go along with it. We've got the three things: the vertices, the faces, and the edges, all to contend with. And I guess if you remember the tables that I wrote up on the board, I'm going to regurgitate them again today, but the one that had the most stuff in it was the edge table. And that's really sort of what this particular data structure centers around, is the half edges. But so I want to redo the tables that I had from yesterday. So this is yesterday's DCEL tables, and they were short and sweet, and I'll keep them short and sweet. For the vertex table, we had the vertex, we had the coordinates. I'm not going to even mess with that, and then the edge. The incident edge, and we just had X, Y, Z, and W. So let me just make a little table out of this. And I believe the way that I filled it in, the edge that you pick is arbitrary, but I believe these are the ones that I had yesterday as the. It's not arbitrary, but it's an arbitrary edge that emanates from that vertex. And so that was presumably what I had. The face table looked like this. It also is an arbitrary choice on which edge goes along with it. We had the two internal faces that were inside that triangulated polygon, and then the external face. And I had arbitrarily picked these edges, I believe, as the edges that went along with them. And then the rest of the junk was the edge table. And I'm not going to regurgitate the entire edge table, because I just simply want to have this stuff up here to sort of motivate how things went. So the edge table looked like we had the edge, we had the origin vertex. So we're talking about the half edge table here, but this would be the origin of that half edge, the twin edge, or twin half edge, the face associated with it, the next half edge, and the previous half edge. And we had that triangulated polygon had 10 edges in it, or 10 half edges in it. So I'm going to spit all of them up here because I want that part, but I don't necessarily want to fill the rest of the table in. Just for reference sake, that foregon looked like this, and we had X, Y, Z, and W, and this was F1, F2. I don't remember what the actual edges. We labeled them somehow. This was E1. This was E4, 2, 3, and 5. So, and then we had the half edges, the one side, the one side of each of these was inside, and the to side was outside as we went around, except for, of course, the one that's in the middle. But to add what I need in this edge table, let me just, we have a row for every edge, and columns for each of those aspects of the edge. So my origin here was what? It was Z for this one, and X for this one. I'm not going to mess with the rest of it. Its twin was E12 and E21. These two are twins with each other. The faces here are F1 and F3. Next and previous, those are edges that, as you go around the face, so this was E51, 5, 1, and E42, and then E41 and E22. And we have filled in the rest of this stuff based on the way that I've drawn the half edges around this thing. So that's, if we think about implementation, we need to implement so that we have the connections between all of these. We obviously have the vertices connected to the edges and vice versa. Vertices connected, the edges connected here and vice versa. And we need to do a representation that reflects that. So an edge, or a half edge rather, is a row in this, and that row has a bunch of stuff in it. So a reasonable thought is we do objects. I mean, and that same idea present in the other tables as well. We'd have 3 objects, one for a type for each of these 3 tables. That is, we have vertex objects, edge objects, G, E, and face objects. I guess Python and C++, we both think of objects as you know, an amalgamation of things. The old term for that was record, which sort of arose from the distant past, actually from COBOL days, and that concept of gluing things together to make, you know, one entity out of a bunch of not necessarily same type data is what COBOL referred to as a record, and that idea persisted at least through the language that preceded C as the popular language, through Pascal and Modula. They used record as the term. So in a lot of the literature that you look at, you'll see the term record, where we think of now the term object, bringing things together. But basically our vertex objects, basically an object of each of these 3 types is going to be what we need for a row. So the vertex object, for a row in the vertex table, we really sort of have this coordinate business is like local data. And the edge thing is a link to the other table. So let me just write it as coordinate and then an index to the edge table. And the same sort of thing for the face. You know, we talked a little bit about things that you could have as like local data for a face, like a color or, you know, maybe a texture or something like that. If we were doing something beyond this, but the significant part here is also an edge, and so, you know, an index to an edge in the edge table. And then thinking about the edge object. So I've got 1, 2, 3, 4, 5 things. So I don't know if I can draw a decent. So my edge object would consist of the origin, so a vertex index. My twin, so that's an edge index. My face, the face that the edge, half edge corresponds to, so that would be a face index. And you know, you see how all of these guys now connect with each other. Both of these last guys are edge indices. And bingo, everything is now sort of connected together. If I go and if I index my table, each of these tables appropriately, and so do like that, and pick out this information right here. My entry is going to look like my origin vertex is X, which is vertex 0. My twin is the other guy is also 0. My face is F3, so that's index 2. And my next and previous are 4, 2, which is 7, and 2, 2, which is 3. So, you know, in order to connect these guys together, it's simply just a matter of relating the data that we have in the table with the index in the appropriate other table. In fact, you know, I did it in terms of indices because it's easy to think of, because we visually got the tables up here on the board. But you know, we could just simply group this idea and put pointer in all of these cases. So, you know, index could become pointer. And suddenly we've got a linked structure. Suddenly we've got the connection via links. And in fact, there really isn't anything. I've done this as a table and consequently got the sequential representation out of these. But in fact, each of these could be a list of objects of the appropriate type. So that in fact, to actually implement this edge table, I'd have all of this stuff plus, you know, thinking of as pointers. Let me just cross that out and say pointer in all of these. And then this would be a pointer to my next one of these guys in the list. So I would you know, I would point from here to an appropriate one of these, from the face to an appropriate one of these, and then each of these would just be a pointer to someplace else in the list of.
So if we're pointing, we're just pointing to the next. Is this list here sorted, like your edge table, in any way? Like you got E1, E11, E12, E21.
Not necessarily.
Okay.
It certainly could be, but there isn't. We don't really do anything with the linearity of this, except to hook them together. What we do care about, though, is, you know, which one it is that, you know, this one, except for the twin aspect of this and them being adjacent to each other, the rest of this stuff that hops all around down here. So really all we care about is, you know, who it is that occupies that relationship. Sorry, I closed the door, Stanley. So, you know, so it's not particularly intimidating to try to construct a representation for this doubly connected edge list. So my point is we have plenty of tools in order to be able to implement one of these things, either as arrays, which have, you know, the ugliness of an array, or as some sort of linked together structures, which have, well, the trade-off is a linked together structure is going to have overhead, because links themselves, you know, a pointer to something is generally fairly large, anywhere from 4 to 10 bytes. So that's, you know, and that's pure overhead. But in any event, we've got we don't really need any additional tools in order to construct these things. I want to look at what kind of operations we might need. So in Stanley, in C++, we have, when we make a class, we make a constructor, which basically just initializes the idea is that we're constructing a data structure here. So this would like initialize it. It would like make an empty array, or make your pointers initially null, or make them have something to point to, or whatever, but initialization. And so a reasonable question is, what does it mean? Now, I don't know why I've got the buzz. I don't have my fan on. I thought it came about pretty quickly this morning. So what does it mean to construct a DCEL? I mean, I need to initialize the 3 tables, whatever that means. I mean, they could be empty arrays, which means that, you know, however the arrays are filled up, I'd have to have, you know, something that indicates their emptiness. So probably, you know, an initial index or an occupied last slot being 0. Similarly, if pointer is the representation, yeah, I'd have pointers that are empty, are null in the C++ terminology. I don't know what the default for pointers in Python would be. But you know, initialize totally empty. So this would correspond to like a 0 parameter constructor in C++, the default constructor. But when we make one of these, we're really going to make it in order to accomplish something. So probably we would construct or initialize to some sort of initial configuration. And so then we'd have to think about, you know, what does that mean? So the question here is, what's an initial configuration for the for the non-default construction of one of these things. So that makes us have to think about, you know, just what is a DCL for? It's for a planar subdivision. By that I mean, you know, a division of the plane into chunks, like we've been doing, like we've been triangulating, you know, polygons. So in fact, an initial configuration, an initial non-empty configuration, should be an initial planar subdivision. Well, you could think of a line as in, you know, infinite line extending infinitely in both directions as a planar subdivision. But in fact, what we've been talking about is subdividing the plane with line segments. So really, we're talking about, you know, things that have finite length rather than infinite length. So if I'm going to subdivide the plane with line segments, the smallest that I can get, I haven't subdivided the plane here with a single one. The smallest subdivision I can get is a triangle, where I've got an inside and an outside, where I've got a closed chain of segments. And so really our initial, except for the default, the smallest initial configuration I can have would be 3 edges. So that means 6 half edges, right? 3 vertices. So that would translate to 3 vertices in the DCL as well, and 2 faces, the inside face and the outside face. So really, my 3 edges, it's the 6 half edges that would be in the smallest initial configuration that I could make. Yeah. Okay. So we have default. We have non-default, minimal non-default constructor, and I guess to go beyond this. So this is the least I could do. Beyond that, I would want to construct from a set of vertices, a set of edges on those vertices that connect the vertices into a planar subdivision. And a set of faces of that subdivision. But it would have to be a subdivision. You know, it would have to be something that actually has interior and exterior in that subdivision. So this would be like the base, the simplest such. I guess. Well, actually, I guess the empty one would be the simplest such one. But this would be the first trivial one, non-empty one. So. Lots of times when you think about the construction process, you think about what the
smallest non-trivial would be. And then you think about how then you would construct a larger whatever from that smallest one. And so we might talk about adding edges and adding vertices and faces. So let's consider adding an edge. So this would mean two half edges, of course. So an edge, something that has two half edges, is gonna require vertices for it. And I've got a picture drawn here that's not probably better to stick with it. So let's suppose that we've got vertices A and B that are already present, and so consequently they have, you know, their corresponding half edges or edge that's incident to them. And so I'm just going to have this, and down here for B. So this corresponds to a single edge. The two half edges that correspond to that single edge, and the same sort of thing down here on B. Just I've got something to go with. And so it's got a I guess it would be a half edge going that way and a half edge going this way, and so on. And we've got this face that's in between, and the rest of this planar subdivision continues out. So let's suppose I want to add an edge that goes from A to B. So I'm looking at adding in this new guy. And so that means I'm going to add in, I will necessarily have to add in the half edge that goes that direction and the half edge that goes this direction. The half edge that has origin at A and the corresponding half edge that has origin at B. That's also going to split the face. So I've got a new smaller face. They're not the same face. So maybe this is face prime and this is face double prime. Just so that we have names for things. So what effect that has on the data structure is actually, I will have two new, so I get two new half edges, so two new entries in the edge table. And of course, that means two new half edges. I get the new face. All right, so so I'm going to have to follow half edges from A to B and B back to A, updating the face information. From I guess it's going to be from B to A. I'm going to have, you know, face prime, and from A around to B, it's going to be face double prime. So the B to A, I get the new, what do I call it? F prime. And from A to B, I get the new F double prime, the new face that results from that split. I'm also going to have to, let's see, is there anything else I have to do going all the way around? I have to update. So this amounts to iterating all the way around. I also have to update, I guess it would be So A is a vertex. So A's edge, the edge that emanates from A, I'm going to have to update his previous. That's going to have to be the new half edge. The new So by that I mean here's A's. Did I say that right? A edge previous becomes this guy. A's A's edge previous was this, and now it needs to become this. So how can I say that nicely? Let's say this is let's say this was EK2 and EK1 and EN2 and EN1. And now this is the new guy, so I should have used N for new. So how about M1 and EM2. So that is EK1's previous is EM1. And the same sort of thing for the next, for EN1. So I want EN1's next to be EM2. So EN1's next, this is going to be, this was actually A dot edge dot previous. So A's edge dot previous. So that's next. So next equals the new half. So I think I got this wrong. A's edge previous. No, I'm good with that. A's edge previous. So actually, the order of these needs to flip around. I need to do this first and then this in order to avoid losing what I'm doing. The point of this is this half edge has to get updated. This half edge has to get updated. Similarly, down here, this one and this one have to get updated to reflect the presence of the new half edge. So there are 4 edge updates. There is there are updates for face information all the way around here, and also for all the way around here. There's a new face present, and so we have to update the face table correspondingly. There are no new vertices, and in fact, by updating the appropriate information around this, I get the update necessary for the vertices. But the point is there's quite a bit of work. There's many updates necessary. I think I counted 1, 2, 3, 4, and then all of these and all of these, and then we have 5, 6 for new edges that enter, and we don't have to. So there's 6 obvious ones, as well as an iteration around 2 half faces. So there's quite a bit of work involved with that to add an edge. Let me do next something that doesn't seem immediately
guess I might just start over on this side of the bill. There are a couple ways to add a vertex. Let's suppose for the moment that I want to add I've got an edge, and I want to add a new vertex. So that's this guy right here that's getting added. So when I do that, this edge now changes. So this the existing edge is removed and replaced by two new ones. Of course, an edge corresponds to two half edges, so this is going to be two half edges. And it's replaced now, it's going to be by four half edges, four new half edges. So I have to update some, the next and previous. I'm going to, potentially I'll have to check and possibly update vertex edge information. I mean, if this vertex happened to have this edge listed as its edge, and this edge is gone, I'm going to have to update this vertex, and I probably would pick the new half edge that went down to the new point, or I could pick somebody else. But there's definitely going to have to be updates that take place there. What else? Yeah, faces have edges as well. So, you know, this faces, those two faces, edge information may have to be updated. I believe that's all I had to say on that. But that's one way to expand the vertex set. There's, of course, another way to expand the vertex set. If it doesn't happen to be a vertex that's going to land on an existing edge, you know, my other situation might look like this. And I want to add a new vertex out here. Of course, to do that, since we're talking about representing a planar subdivision, just simply plopping a new vertex in place isn't a planar subdivision. If I'm going to add a new vertex, that means I'm going to have to also add the edges that keep it a part of the planar subdivision. So in fact, adding a new vertex out here, I'm going to have to also add the incident edges. So it'd be a vertex and two edges, or a vertex and four half edges. So there'd be, you can view it either as 3 inputs or 5 inputs, the vertex and appropriate information to link it. Of course, those links will have to go to existing vertices. So that could be a vertex and 2 linked vertices, or a vertex and the 2 edges which go to it. So there's face information that has to be updated. This external face may have as its edge the edge that's inside here. So you want to update its edge information. You also have next and previous. You also have a whole new
face to be added. So there's a bunch of things that that need to be updated. So again, the point is there's work involved in doing an insertion. And then finally, for removal, if I'm going to remove a vertex, I'm going to have to remove the incident edges that go along with it.
So when you just drop it out in space away from the shape, are you just picking the closest two vertices to link it to, or?
No. The point is you can't have just a vertex by itself out here in space.
Right. Oh, so you're already feeding it. You're giving it the information.
Right.
You're deciding when it lands.
So we would have to know at the time that this goes in what it's connected to. And I just, because this was convenient, I just do it like that. But we basically need to know. You can't simply add a vertex to one of these things because it's a representation of a planar subdivision, and consequently anything we add has to maintain the idea of a planar subdivision inside it. So I'm going to stop at that point for a couple of reasons. I've got too much of a buzz going on, and really this is as far as I wanted to take this idea of DCEL until we actually need it for something. The programming project for this week won't include DCEL. It's going to be a triangulation problem that I don't yet have put together. So it's probably not going to get posted until tonight or tomorrow. And I'll ping you guys when I get it out there. I was looking around for DCELs. There are a bunch of C++ DCEL packages. There's a good one from the Computational Geometry Algorithms Library that seems to be able to do absolutely everything. And as a result, it's kind of hard to figure out how to use it. There are a bunch of much simpler implementations on GitHub, as well as on a couple of other code sharing websites. I found a code sharing website called My Shitty Code, and I stumbled on it purely by accident. It's not just one person's shitty code. It's a lot of people's code that's on it. And it looks like it's pretty good, but it's not necessarily directed at things that we're doing. It's a little bit more like code for, code for things that use computers that you can, in a manner that you sort of set up parameterized stuff for. Like there's a bunch of Excel spreadsheets out there that, but there are also some good image processing things out there as well. I found at least 3 Python implementations of DCELs, and that actually didn't surprise me very much at all, because many of the places that Python landed initially in, I don't want to say commercial, but in non-academic situations, were things where graphics were pretty heavily involved. So it didn't surprise me that there were DCELs all over the place for Python, and generally pretty nice looking. So in any event, whatever language we're programming in, there are DCEL packages that we might be able to use. The programming project, though, isn't going to involve that. It's going to be a triangulation problem that won't use the triangles beyond simply having them. So there we go. I guess have a nice weekend. I don't know what it's going to be like in Ames, Stanley, but it's going to be hotter than the dickens here. And when I lived in Ames, whenever it was hotter than the dickens here, Ames was just like that squared or beyond. So I hope you got an air conditioner.